This is unit 8.7 and 8.8. We're going to be learning how to take volumes of 3D shapes by cross sections. In the last few lessons, we have found the area between two curves, similar to this. Now we're going to apply this and use this to actually help us calculate volumes. Right? So we are using volumes using cross sections, and you can see here that if you notice these 3D shapes, they're split into little pieces. Like here, these look like they're split into quarter circles. These are split into squares. These are split into triangles. And these are split into rectangles. So those are the cross sections we're referring to. It's like if you take a slice of a 3D figure, you would see a shape, and that's called the cross section. And we consider these cross sections as our base, and then that's what we're going to do the calculus with. And we always find the volume using a definite integral, because if you remember, definite integrals mean to add up the area of all the shapes. Or I'm sorry, excuse me. If you have a curve here and you break these into tiny rectangles, right, the integral is basically the sum of all those little rectangles. And so when we do the definite integrals of cross sections, we're adding up all of these little cross sections to find the volume under the curve. Now, here's some important notes about cross sections. You're always going to do a definite integral. There will always be boundaries. Normally, we use rectangles, but there can be any shape. Like you can use quarter circles, you can use triangles, squares, but most of the time we use bases. So we'll just always, we use rectangles, so we're just always going to like defer to those shapes. So your rectangle will be your base. Now, here is an important concept. In your problems, it's going to tell you that the cross sections are perpendicular either to x or y, and that is your hint on where your integration takes place. Sometimes, like if you look at this, the cross sections are perpendicular to the x-axis, so we're going to integrate with x. Same thing here. But if you notice this one, it does even say that we are perpendicular to the y-axis. So when we do the cross sections, we're going to integrate with y on this one. So you do have to be mindful of that terminology. And then some problems that I have found will give you the area without mentioning the shape, and it just wants you to write the integral. So here's kind of our format. You're always going to have a representative shape, most likely an integral. It's always going to be perpendicular to some axes. You're going to set up the integral, and then you're going to find the area of the shape, whatever shape this is. And then there will always be boundaries from A to B. And again, this depends. You always do dy or dx depending on where you're perpendicular to. So with all of that, let's look at this shape. This is an equation. It looks like it's a parabola of some sort. And notice that these all little green lines are the cross sections. But if we move, notice how that each cross section in this example is a rectangle, right? And notice like if you're over here at the very left, the rectangles are small and they keep increasing as you go to the right? So the rectangle here is small, and as you keep going through the figure, the rectangles keep getting bigger. And so this is kind of our shape. But when we do the calculus, you're going to find the area of the square and then use an integration with that. We always have our boundaries. In this case, A and B. Our A is, I think that's supposed to be -10, and our B is 10. Right? And if we kind of move these around, we're going to have another 3D shape over here. But that's kind of visually what we're doing. But that orange rect square is what we find the area. And then when we take the integral, it's going to add up all of these areas to make that shape. Okay, so example 1, we are actually going to find this one in our calculator. And then the other two examples, example 2 and 3, we just set up the problem and we don't even do them. Oh, and I just noticed. Hey, Cindy, thanks for the drawing. All right, so here we go. Let's look at this problem. It says R is the shaded region that's bounded by those two graphs. The region R is a base of a solid. It is perpendicular to the x-axis, so we know from this information alone, it is going to be dx. So we're looking for x's. And we are using squares in this example, because it does say is a square. So if you look here, I will try to draw this to the best of my ability. Again, I am not very good at drawing this. But basically, if we draw a square here, and then maybe a square here, you can kind of see that the 3D shape is going to be like a cup with a curved edge, right? And so since we are using a square, the only thing we need to really solve for is this square. So we need to find the area of this square. So let's write our notation out, right? So our volume is going to always be the integral from a to b. We don't know that yet. And then we're going to get something with dx. Now let's do a little work here. Because our cross section is a square, we know to find the area of a square, it's going to be side times side. And then we're going to have dx. And where this is coming from, I will show you this on the picture, right? So again, if I want to find the volume of this 3D shape, I need to find the volume of a little tiny square. So basically, if I can find the area of this square, or this cube, I guess it's what it's called, and then I'm going to take the integral of all of the little cubes that are right here. Now, I will say that this width is what we call dx, and so that's where this comes from. That's this part. And then all we need to find is the area of the face, which in our case is going to be side squared dx. So now, how do we find the side length? Well, if we come back actually down to the 2D picture, this little height is really one of the sides. This is the side length right here. Now, how do we find this on the picture? Well, if you notice, we notice that this part is 1 unit in length because you have 1 minus 0. We know this length is 1/2 because it's 1.5 minus 1. So if you want to find this side length, it's going to be this equation subtract this equation. So our equations are e to the negative x and then minus 1 minus cosine of x. And again, this is squared dx. So this, again, this is my side length that I found because it's this equation, subtract this equation, and then I square it. The area is side squared, so that's why we squared it. And the dx is really the depth of the cube. Because again, the volume is going to be length times width times height. Length times width, and then the height is dx. But since this is a square, our length and our width are the same. And so that's exactly what it is. So this is what our integral is. From here, all we need to find is our limits of our integration. So we're starting from here and going here. And so it looks like this is from 0 to 1 or close to 1. I don't know if that's actually equal to 1. So let's figure out what that is. Okay, so how do we determine this? Again, this will be done in the calculator. Basically, this intersection point are where these two functions are equal. And if you type this into your calculator, you could type this in as one equation, y1, type this in as y2, and then find the intersection on the graph. And you're going to get that that is about 0.9419. And so that is our limits of integration. So this equation is going to be e to the negative x squared minus 1 cosine squared, or 1 minus cosine of x, all squared. And you will just do this in your calculator. You will not do this by hand. And just to reiterate one more time, we're going from 0 to the 0.9419. And I found that by setting these two equations equal to each other in my graph and finding the intersection point. And then we're squaring because we're trying to find the surface area. I keep saying surface. The area of the face, which is side times side. So that's why it's side squared. And then this is one side length. I found that because it's this equation subtract this equation. That's how you find the height here. And then type this into your calculator, and that you will get that the area is approximately 0.46106. Or that the volume. I said surface area, but I meant volume. And there you go. This is the only problem that we actually do in our calculator. The rest are just setting up. Okay, so again, here we go. We have this graph. Notice that these are two composite shapes. And it does say let R be the region in the first quadrant bound by the x-axis and these two graphs. And it says region R is the base of a solid. For each solid, each cross section is perpendicular to the x-axis. So this means we're going to use dx. And it is a square, right? But do not evaluate the expression. Okay, so we are going to have two separate integrals here, because again, we have squares that look like this. And I guess let me try to draw these to the best of my ability. So again, we kind of have this 3D graph that kind of looks like, so we kind of have the left side of the graph that's left of that dashed line looks something like that. And then we're going to have the right side of the graph kind of looks similar. I don't know. It's just going to be a triangle. I don't really want to draw it. I'll draw the next one. We have two separate integrals. We have to do the integral of this one and the integral of this one. And this is still an area between two curves, just like our previous problem. It's just our curve down here is going to be y equals 0. So like this first integral is going to be the log of x, right? So when it's going to be log of x minus 0. And this integral is going to be 5 minus x minus, again, 0 right here, right? So because that's there. So let's mark this. Let's say this is, I don't know, volume 1. This is volume 2. So basically, we need to add these two volumes together. So there's two separate integrals we need to write. All right, so let's take volume 1 first. So again, we're going to have a square. So this is going to be side squared dx. Looking at this square here, how do I find this side length? Well, really, it's just going to be the top curve minus the bottom curve. The top curve is log minus 0. So this is going to be log of x minus 0 squared dx. And again, this is volume 1. Volume 2 is going to be this square. It's going to be the same thing. It's going to be, but it's going to be over here. This is going to be 5 minus x, because that's the top curve. The bottom curve is 0. So it's going to be this value minus 0. And really, so this is just log of x and 5 minus x. And that's kind of it. So this is like my volume 1. This is my volume 2. The only thing is we need to find our value of integration. So again, in your calculator, you're going to set log of x equal to 5 minus x. And that's going to give you that it's about 3.6934. And so that's going to be your value here. So the integral of this first volume is going to be from 1 to 3.694. And the equation is going to be log of x squared dx plus your volume 2, which is going to be from this value to 5, and it's going to be this minus 0 squared. And there you go. That is the integral that you would need to type in to solve. And some of the questions are like this, where it doesn't even want you to find the answer. You just set it up. And you could type that into your calculator and find the answer if you need to. Okay, so this one is slightly different, and I'll show you why. So it does give us our equation. This is e to the 2x. That's the equation there. And it's bounded by the graph and the line x equals 1. Now, it says the region R is formed by cross sections perpendicular to the y-axis. So we're going to need this in dy. So everything needs to be in y. And it says write but do not evaluate the integral. So the volume is going to be the integral of something, but we'll get there in a second. Now, I want to do a visual on this one because it's really good too. So if I draw these as squares, my first thing I noticed is we have kind of a cube that we can find the volume to, because the volume of this piece is going to be 1 cubed. And then plus, and here I'll show you down here, right? So this right here, we've already found the volume to, but we still need to do the integral of this area here. And this one's slightly tricky in that way because you can't, because since we're doing dy, it's going to be from since we're integrating with respect to y, because everything's perpendicular to the y-axis, our integration is going to be from 1 to e squared, but we're still left with this volume piece that we see. Now the rest of the volume kind of looks like this, which looks like kind of like a curved cone, right? It's like a curved cone, and then you still have this block that's right here. Okay, so let's erase that. I just wanted to give a visual, but we do need to keep track that we do need this volume of r. So we're going to have this 1 cubed. So let me just write this over here now. Okay, so now we do need to find the volume of that shaded, or the volume that has the base of that shaded region r. And again, everything needs to be in the variable y. So let's kind of think about this first. So again, these are going to be squares that are coming out. So again, that's side times side, so side squared dx. But again, we're supposed to be in y. We're supposed to be in y. So this is supposed to be, dy. Okay, so how do we do this? Well, we know that our equation is y equals e to the 2x. So let's write this in terms of x first. So we know y equals e to the 2x. So we need to solve for x in this equation. The way to do that is to take log of both sides. These logs cancel. So we have log of y equals 2x. And then if I divide by 2, I'm going to get 1/2 log of y equals x. And that is my key piece. Okay, so now how do we find the side length of the square? Well, the side length is going to be from here to here. And it's the same way we did before. It's going to be the upper value minus the lower value. So if we want to find the side length of the square, it's going to be 1 minus whatever x this is. So again, 1 minus x. But again, we don't need x's. We need y's, because y is our differentiation. So we need to make this substitution in for x right here. And that's it. So that's our side length. Oh, and square it. I forgot to square it. So our integral is going to be 1 minus 1/2 log of y squared dy. We just need to figure out the boundaries. And what are our boundaries for y? We're integrated from 1 to e squared. So from here to e squared. And that is the integral setup. If you wanted to, you could type this into the calculator and solve. So kind of a little tougher because we did have to do it with y. We had to convert to y. And that's all 3 examples. The next kind of thing I just want to cover really quickly is just the different types of shapes you'll use. And we're going to do different types of shapes with this as our base. We don't know what f and g are. That's not the problem. We're always integrating from 0 to 1. And we're assuming that we are perpendicular to the x-axis, which means we need dx. So if we were integrating with squares, like if there were squares here, all we have to do is find the side length squared. So this side length is just going to be the top function, subtract the bottom function. So if we were setting this up, this would be the integral of 0 to 1. And again, that's going to be the same for all of our problems. And this is going to be, how do we do this? This will be f of x minus g of x all squared dx. And that is it. So if we're using squares, that's our integration, and whatever f and g are would go in there. Now quarter circles, so let's do a quarter circle. The quarter circle, the area is going to be 1/4, because it's a quarter, pi times r squared. So our volume is going to be, the cross section is going to be 1/4 pi times radius squared times dx. Now we do need to figure out this radius. What is this radius going to be? So if we look here and we think of this as a quarter circle, right? So it's still this length, is still just f minus g. Because again, that's a radius and that's the same radius, right? The shape would look different, but the equation would be the same. And so my radius is just going to be f of x minus g of x, and then squared dx. And then if I wanted the volume is just going to be the integral of that function. And I did pull 1/4 and pi outside because it is a constant. And I did forget, this is from 0 to 1. Now what if I use semicircles? So semicircles are basically half circles. So the area is going to be 1/2 pi r squared. Now what is the radius of a semicircle? Now this is slightly a little bit more tricky, so let's draw it. So be careful here, because this length is going to be f of x minus g of x. But in our equation, we measure the radius here. So basically, we need to divide this by 2, because f of x minus g of x is this whole length, and we only want half of it. So I'll write that this is the half of the diameter. And then if I substitute the diameter in, and that's kind of it, we can technically square this and square this. This will be 1/2 pi times a quarter, because again, that is what 1/2 squared is. And then just leave this as is. And that's our equation. We just have to take the integral. So I'm going to take up a lot of space here, but the volume is going to be, and I'm going to pull this outside, so that turns into 1/8 pi, and it's f of x minus g of x squared. So that would be the volume using semicircles as our cross sections. Okay, rectangles with height 4. So that means this is going to be 4, and that's the side length. Now, the area here is 4s. So my volume is going to be the integral of 4, what we call s dx. And then what is our side length compared to x? Well, again, this side length, that's our s. That's just going to be f of x minus g of x. The height of 4 are these two sides, right? So it's just f of x minus g of x. So this is 4, and this is f of x minus g of x dx. And then you can rewrite that and put the 4 outside. And that is it. This one is not squared, because again, the area was 4s dx. Okay, rectangles with height twice its base. So again, we have a rectangle. So we have side, and this is 2 times the side. So the area is going to be 2 times the side squared. So if I want to find the volume, it's the integral from 0 to 1 of 2 side squared dx. And again, the side, coming back to here, this is just going to be 2s instead. So this height is going to be f of x minus g of x. So I'm going to pull the 2 out in front, and this is going to be f of x minus g of x squared dx. Now, what happens if we use an isosceles triangle? Let's erase all this. Now, an isosceles triangle means that the two bases are the same. So this will be a side and this is a side. Because that's what isosceles triangles mean. That this length is equal to this length. We'll just call them side again. So those are congruent. We'll just call them sides. And so my volume is going to be the integral from 0 to 1. Now, how do we find the area? It's going to be 1/2 base, which is the side, times the height, which is also the same side, dx. So if I pull the 1/2 out, I'm going to get 0 to 1. And then let's find the side length. But if we come back up here, the side length again is just f of x minus g of x. It's going to be f of x minus g of x squared dx. And there you go. So that is one example with all of the different side lengths. The only ones that were somewhat tricky was the difference between the quarter circle and the semicircle. And the reason why is the quarter circle is kind of similar to the triangle. But notice that the radius is the full length from here to here. So that's why we still just use f of x minus g of x, and that's part of the quarter circle part. A semicircle does this, but notice that the f of x minus g of x is the whole thing, and we want half of it. That's why we took half of here. And this is the only one that wasn't squared, because rectangles, it's going to be the side times 4. So this area is 4s, and then the depth is dx. So it's 4s dx, so there is no square with the rectangles.